Okay, last time we talked about features and we talked about clustering so we could classify different types of, in this case, sounds. So as you may recall, we were trying to discover automatically, letting our computer monitor to see if our neighbor is playing loud music. So in order to kind of calibrate our system, figure out how all this is going to work, we started by collecting examples, and then it became obvious how we could do a dividing line. So, for example, I'm going to say spectral peak prominence, meaning do we have spectral peaks that stand out from the rest of the spectrum, or is the spectrum rather uniform or smooth with no one frequency standing out? So this tells us, do we hear a specific pitch? Do we hear a specific tone? And then we had energy on this axis. And we found that, let's see, and I'm going to try to draw this in different colors. So we found the loud music tended to have high energy and strong spectral peaks, whereas noise had probably lower energy and no prominent spectral peaks, whereas a passing car or truck may be somewhere in between. Let's do that in blue. But sometimes the music can be varied. How many, this is the question, how many samples do we need to have before we have a pretty good idea of where our dividing line should be? Well, it depends on several things. One, if the samples are very, very separated, we might need only a few to start seeing the pattern. If, like in this case, there's some overlap between them, it might not be clear where the best dividing line is going to be. So as we fill in some more examples, maybe things are getting a little bit clearer. Turns out that that car noise right here was a little bit anomalous, and so whereas if we just had that as one of our very few examples, we might have had a hard time picking out how to divide them. But at this point we'll say it seems to be pretty apparent that we could draw a dividing line something like this. We're going to get that one highlighted example wrong, but all the rest we're going to do a pretty good job with, and it works out. So we've come up with our little detector. How do we actually implement this? Well, we'll talk about that more a little bit later, and actually ECE 6254 and 6250 both talk a lot about these types of things. But for now, let's just assume we can draw a line and we can determine if we're above or below that line. Because we're going a different direction, and that is, we now have two dimensions and it seems to be useful. What happens if we add maybe a third dimension? Maybe we wanted to find out the temporal variation. Music presumably would vary a lot temporally, but the car would be slowly varying. It would or something like this as it passed by. if we add that third dimension, it might enable us to resolve what happened with our misclassified highlighted example there by spreading it into more dimensions. Well, this is great. Let's just keep going to higher and higher dimensions. We have this problem, though, when we do so. I'm not saying we shouldn't. I'm just saying there could be a problem. That is, as we add features, dimensions, we're now at 2 dimensions. Going to adding another feature would take us to 3. We may be able to better separate different classes. There's a downside, though, and we're just racing through this, and that's called the curse of dimensionality. If you have dimension equals 1, you need just 2 features, one here, or 2 samples, and one of each possible example, and look at that. We can come up with the dividing line to separate them. Maybe it's not the best, but we've got something. But what happens if you go to 2 dimensions? If we go to 2 dimensions, then we need at least 4 samples to give us binary comparisons every direction, in each direction. Another way of thinking about it is, as we go to higher and higher dimensions, the volume gets larger and larger. With the larger volume, in order to kind of fill out the shapes in that volume, you need more samples, more examples. So with 3 dimensions you go up to 8. If d is equal to 20, we need approximately 10 to the 6th. But this is just for simple binary comparisons, right? If we want something that's much more fills it out and tells the story like the plot we have up above, the data requirements become absolutely enormous. So what do we do? Let me just write this. As the dimensionality increases, the amount of data required increases exponentially. Okay, so we're going to talk about how can we reduce the dimensionality of the data. There are several techniques. One is feature selection. So back to our example of the neighbor playing loud music. We have some things we could do. We could keep adding features. We talked about adding the temporal variability. Maybe we want to add the spectral shape by sampling the spectrum at, say, 16 points and using those as features. So now we have our spectral peak prominence, we have our energy, and we have the temporal variability. We've got 3 dimensions, and we add 16 more for the spectrum sampled at different points, and so now we're up at 19 dimensions. And so you can see how the dimensions grow really quickly. To use this example of adding the spectrum, it's pretty easy to see how the energy might increase as the level of the noise increases. And so as we go over to the, we have loud music, we move over to the right on our energy plot. Spectral peak prominence. We know that music tends to have pitch, tone, notes, so we expect to see some spectral peak prominence, and so we know it's going to go up. But what about the spectral shape? Well, music is going to have, depending on where you're at in the music, what's going on, what instruments are playing, many different spectral shapes that it could have. Those spectral shapes are going to largely be different from the many different spectral shapes that pure noise can have or a passing car can have. But the variety is huge. And so in order to get examples of all the different things that we could have, we need a lot of examples of music. So we would probably have to let that sit there and record for hours and hours as our neighbor plays music, and hours while there are just different types of background noise, birds singing, cars passing, and the general background noise that exists in the world, air conditioners, whatever it might be. Well, this could be a problem because now we need so many more examples before we can even start to come up with a classifier. So what we're going to do is we'll add all of those in there, and then we'll start looking at them and say, we could individually say, you know, this particular feature, the frequency at 2000 hertz maybe, doesn't appear to be very helpful. So let's get rid of features that aren't very useful, redundant or unuseful features. So that's one approach. Approach number two we're going to talk about is, and this is where we're going to spend most of our time, and this is feature extraction. Feature extraction means that we take all of our features and we come up with new features that are linear combinations, perhaps, or another way of thinking about it is features of the features. So in this case, we compute new features based on the old. How do we do this? Well, there are a variety of ways, and I hope that this just points you to some of the opportunities, because we're only going to look at one in particular, and this is just to provide some good examples. Principal component analysis in the next lecture.